Well, this topic involves looking basically at some other trig relationships, how we can manipulate our trig functions. So the first one we're going to look at is the sum and difference of angles. And there's different ways of creating these formulas, but this is one way. Here's our unit circle, radius 1 of course, and I'm going to call that point P, and there's a right angled triangle. I'm going to call that angle beta. So there it is, and I'll give that an x coordinate and a y coordinate, and so then I can use simple trig to say x is the cosine of beta, and the y coordinate is the sine of beta. Now it doesn't matter where I put the point is always going to be the cosine of the angle and the sine of the angle, and that angle being the angle it makes with the x-axis. So I could put another point over here, Q, so that obtuse angle there is alpha, and that would be the cosine of alpha and the sine of alpha. And you might be thinking, but hang on a sec, surely that should have a negative coordinate for x. But if you think about it, if alpha is an obtuse angle, well, the cosine of alpha would be a negative number. So cos alpha is negative and sine alpha is positive. So I've got these 2 points. I want to find the length of PQ. Now, I can do it by trig. We could use cosine rule and say PQ squared is 1 squared plus 1 squared minus 2 times 1 times 1 times, and that angle would end up being alpha minus whatever beta is. So cosine alpha minus beta, which tidies up to be 2 minus 2 cos alpha minus beta. Or I could do it with coordinate geometry and use our distance formula, in which case I'd get PQ squared is the difference in the x values squared plus the difference in the y values squared. And if I expand that out, I get this huge expression. But I notice things like I've got a cos squared alpha and a sine squared alpha. Well, we know they add together to give 1. And there's a cos squared beta and a sine squared beta. Well, they'll add together to give 1. So I could simplify that to be 2 minus 2 cos alpha cos beta minus 2 sine alpha sine beta. And here's where I'm going to have to break the news to you. I actually lied. I couldn't care less how long PQ is. All I really wanted with these 2 expressions for PQ squared, if they're both equal to PQ squared, well, they must be the same thing. So now I can say, well, 2 minus 2 cos alpha minus beta must equal 2 minus 2 cos alpha cos beta minus 2 sine alpha sine beta. And I come up with our first little relationship there, that the cos of alpha minus beta is the cos of alpha cos of beta plus the sine of alpha sine of beta. So it's not like algebra where I can just expand the parentheses out. And I think that's probably the most common mistake when people first see something like this. They think, well, cos of alpha minus beta, surely we can just expand out and go cos alpha minus cos beta. Well, no, you can't. We need to use this formula. But now I'm going to do something clever. Instead of having beta, I'm going to replace it with negative beta. And by doing that, I create another formula. Because cos alpha minus beta becomes cos of alpha minus beta, so cos of alpha plus beta. And we get cos alpha cos minus beta plus sine alpha sine minus beta. But then we play around with odd and even functions. Okay? Remember, cos is an even function. So the cos of negative beta is the same as the cos of beta. Sine was an odd function. So the sine of negative beta is the same as the negative of sine beta. So now I can rewrite the formula. Cos of alpha plus beta is cos of alpha cos beta minus sine alpha sine beta. They're very similar formulas when you look at it. When I have minus on the right hand side, I've got plus. When I have plus on the right hand side, I have minus. So how do I remember this? I could summarize it like that. So you can see, well, over here it's plus minus, but on the right hand side it's minus plus. So I remember. But here's how I remember it. Cos, cos, sine, sine. Okay? It's cos, cos, sine, sine. But If it's not the sine function, no, it's the cosine function, it's not the sine function. So if it's not the sine, it's not the sine. So the sign changes. You see? So when we're dealing with the cosine function, because cosine's not sine, so therefore we change the sign on the right-hand side, because if it's not the sine, it's not the sine. So the cos relationship is simply cos, sine, sine. If it's not the sine, it's not the sine. Voila! How easy is that? All right, now what I'm going to do, I'm going to go back to the original one we found out, and I'm going to replace alpha with 90 minus alpha. So now I get cos of 90 minus alpha minus beta is cos, sine. If it's not the sine, it's not the sine. But I'm going to play around with complementary ratios. Cos of 90, I could factorise here and make that minus all of alpha plus beta. And the complementary ratio to cosine is, of course, and the complementary to sine is? So my 90 minus alphas, they can all change. And on the right-hand side, now I have that sine of alpha plus beta is sine alpha cos beta plus cos alpha sine beta. And now I'm going to replace beta with minus beta and do like I did in the last one and play around with odd and even functions. And we end up with the sine of alpha. Again, very similar, but you'll notice the signs are the same this time. So when it's the sine function, the signs are the same. Or another way of thinking about this, whoops. Okay, here's our formula. For sine, it goes sine, cos, sine. So, how do I remember that bit? Okay, I start with whatever function I'm looking at. So when it was cos, I started with cos. And when it's sine, I start with sine. But if I say cos, I've got to say cos twice. And if I say sine, I change to cos. So, cosine function. Cos, I said cos, so I've got to say cos again, becomes cos, so that leaves me with sine. Whereas sine, I go sine, now I change to cos, I said cos, so I've got to say cos again, that leaves me with sine. So cos is cos, sine, whereas sine is sine, cos, sine. Right? Easy, really. But here's the cool bit. If it is the sine, then it is the sine. The signs don't change. Right? So the cosine function is cos, sine. If it's not the sine, it's not the sine. Whereas the sine function is sine, cos, sine. If it's the sine, it's the sine. Well, we can't do sine and cos without doing tan. It'll feel left out. So tan, but I can rewrite tan as sine on cos. And I've got expressions for those, because sine on the top will become sine, cos, sine. If it's the sine, it's the sine. Whereas on the bottom, it's cosine, so we go cos, sine. If it's not the sine, no, it's not the sine. And so here's this lovely expression which looks rather difficult to remember. So I'm going to do something quite obvious. I'm sure you would do exactly the same thing. I'm going to divide everything by cos alpha, cos beta. Isn't that so much nicer? When you remember that sine on cos is tan. And look at all these coses that cancel as well. So cos beta cancels with the cos beta, sine on cos is tan. Cos alpha cancels with the cos alpha, sine on cos is tan. Cos cancels with the cos, 1. And then I've got sine on cos, well that would be tan. Look at that. Tan of alpha plus beta is tan of alpha plus tan beta on 1 minus tan alpha tan beta. Now I'm going to replace beta with negative beta. And again, play around with functions. Tan, was that an odd or an even function? So the tan of minus beta is the minus of tan beta. So I can now rewrite that one. And you'll notice with tan, the sign, whatever's on top is the same, whatever's on bottom is different. Well, How do we remember this one? Well, tan, it's tan plus tan on 1 minus tan tan. Tan plus tan on 1 minus tan tan. Right? Easy. So we can summarise all ours. We have the sine, which goes sine, cos, sine. If it's a sine, it's the sine. Cosine, which is cos, sine. If it's not the sine, it's not the sine. And then we have tan plus tan on 1 minus tan tan. That's just fun to say. Huh? Let's look at some examples. So we want to expand the cos of 2 alpha minus 3 beta, which before today we may well have just gone and said, oh, well, that's cos 2 alpha minus cos 3 beta, which we now know, no, that's wrong. But that's okay. We've got a fun way of doing this. Cos, it's cos, so it's cos, sine. If it's not the sine, it's not the sine. And you make sure you just keep these pronumerals in the same order. You see? And voila! Expand it out. How cool is that? Oh, they're trying to trick me with this one. Simplify tan 20 plus tan 10 on 1 minus tan 20 tan 10. But when I look at this, what do I notice? It's tan plus tan on 1 minus tan tan. Therefore, it's actually just the tan of 20 plus 10, which is tan 30. So the answer is 1 on root 3. So I see that pattern, tan plus tan on 1 minus tan tan. What it also allows us to do is we can find some more exact values now. We know 45, we know 30, we know 60, we know the boundary values. But now I can find sine of 15. As long as the number I can manipulate using numbers that I know. There's lots of different ways I could get 15. I could go 45 minus 30. That would be 15. I could go 60 minus 45. That would be 15. I could go 135 minus 120 if for some insane reason I wanted to do it that way. But I could if I wanted to, but I don't. I'm going to do it as 45 minus 30. Now, it's sine, so therefore it starts with sine. Feel free to say it with me. Sine, cos, sine. If it's the sine, very good. And now we just substitute in the exact values that we already know. So look, sine 45, 1 on root 2, cos 30, root 3 on 2, cos 45, 1 on root 2. Oh, that's nice. The denominator's the same. It's 2 root 2. And so it's root 3 minus 1 on 2 root 2. If sine alpha is 2/3 and cos beta is 1/4, sine alpha plus beta. Well, the really boring way of doing this would be to find out what alpha is, find out what beta is, add them together, and then go sine of that. Keep your fingers crossed that it turns out into something exact and we recognise it. That would be the boring way of doing it. The fun way of doing it. Okay, we draw a triangle. Sine alpha is 2/3. Bit of Pythagoras, other side's root 5. Don't make the mistake of thinking alpha and beta are in the same triangle. They're in different triangles. Unless you get lucky and they happen to add up to 90, but in this case they don't. So cos of beta is 1/4, so the other side's root 15. So sine of alpha plus beta is, of course, sine, cos, sine. If it's the sine, it's the sine. And now I just read off my triangles. And there's my answer. Look at that. And that's an exact value. You wouldn't pick that up on a calculator. Not unless you're very clever. No, even if you're very clever, I don't think you'd pick that up on a calculator. 2 plus 5 root 3 over 12. Ta-da! So 14D, which is in the first book, I think. So let's play with these wonderful new things. And feel free to say that as you do it,